So before we start with all the formal stuff, let's talk about one thing first. And that is, why do we even need to talk about boundary value problems? Well, in the first week, you guys learn about initial value problems, IVPs, which looked something like this. You are given a differential equation on the form y prime equals some kind of expression of yt. For example, that could be y of t multiplied by 2t. And then you were given a thing that was called the initial condition. Which stated, for example, that y of 0 equals 2. And normally this is accompanied by some interval that t belongs to, for example, 0 to 10 or something like that. So this is an example of an initial value problem, and what we spoke about last week was that basically this is a kind of roadmap. You start in y of 0 equals 2, so for time 0 you start in 2, and then this equation tells us how the function y develops over time. Now this week we're going to work on another type of problem called boundary value problems. Now boundary value problems, what they basically are, well, they are also differential equations, but where instead of being given an initial condition as we had in the first 2 weeks, we get boundary conditions. And normally boundary conditions, they are imposed on 2 points. For example, we would have something like y of 0 is equal to some value, 2 for example, and y of 10 is equal to some other value, 5 for example. And now you might ask, like if you're used to working with initial value problems, then you might ask, well, why do we even want to look at boundary value problems? Isn't it enough if I just know where to start? Because come on, the differential equation tells me how y develops over time. And that's also true in the case where you only have the first derivative, y prime, involved. However, not all differential equations are shaped as this thing over here. Not all differential equations are shaped like y prime of t equal to some kind of expression of time and y. This is the typical initial value problem. I should have used green for that, but this is the typical initial value problem. This is how a typical initial value problem looks. However, a typical boundary value problem sort of looks different, and you've probably already guessed, since I spoke about in specifics the first derivative here, that when we talk about boundary value problems, we often look at second order derivatives. So just to illustrate completely intuitively for you guys why it sometimes is necessary to specify a differential equation with 2 conditions instead of just 1 condition, let's try to look at this very, very simple differential equation that I write up here. d2 y dx to the second equals 2. So this differential equation tells me that if I take some function y and I differentiate it twice, then I get 2. And let's just start out with only one condition. I have the one condition that y of 0 is equal to 0. Okay, so what can y be? Now notice in the initial value problem, if I had an initial condition and the initial value problem, then I could determine y uniquely. However, now when I consider this type of problem, then I can't determine y uniquely just based on the fact that y of 0 is equal 0. So the answer to what y can be is actually, well, y can be many things. So for example, y could be y of x equal to x squared. Because then I derive this once and I get 2x, then I differentiate again and I get 2. And also if I plug 0 in x's place, then I get that y of 0 equals 0. So y equal to x squared satisfies this equation up here. However, y could also be, so let's just say y could be equal to y1, which is x squared, but it could also be equal to another function y2, which is x squared minus x. Because, well, let's look at what happens if I differentiate this once. Then I get y2 prime is equal to 2x minus 1. And if I differentiate it twice, then I get the constant goes out and I'm left with 2. I don't know how much of what I just wrote made it onto the screen, but you get the general idea. The general idea is that both of these two functions, y1 and y2, they satisfy this differential equation up here. Also note that the condition y of 0 equal to 0 is also satisfied in this case. And in fact, it would also be satisfied for a third function, y3 of x, equal to y squared minus a half x. So this is why we need boundary conditions for certain differential equations, because without those boundary conditions, the function that solves the differential equation is not uniquely determined. So if, for example, I also imposed the other boundary condition that y of 1 has to be equal to 1, then we can see that y1 of x equals x squared actually solves this problem, whereas y2 of x does not, because it does not satisfy the first, actually the second boundary condition, since 1 minus 1 equals 0. So with boundary value problems, we have a differential equation together with two boundary conditions. And the reason why we need two boundary conditions is because if we only have one, then the solution is not uniquely determined. And also, as you will notice more and more, in most boundary value problems, you will have a second order derivative of y. Whereas in initial value problems, you mostly just encounter first order derivatives of y. Okay, so that was all for the intuition, and in the next video, we will talk a little bit about a specific linear second order boundary value problem and how we propose to solve it.